Okay, we look at section 10.4, day 2, slope and line, tangent lines. We're going to look at the calculus part of the polar form of the equation, polar equations. And so first, to find the slope of the tangent line to a polar graph, we want a differentiable function given by r, which is a function of theta. Okay, to find the slope of polar form using the parametric equations. So x is equal to r cosine theta, but r is a function of x, so it's f of theta cosine theta. Y is equal to r sine theta, which is f of theta sine theta. So when we take the derivative, it's not as easy as you're hoping for. We get the dy dx. We've seen this before. This time in terms of dx d theta instead of dx dt, or excuse me, dy d theta instead of dy dt. Theta is my parameter here, and that's divided by dx d theta. So when I take a look at these derivatives, what's the derivative of f of theta sine theta? Well, I have to use the product rule. So it's f of theta cosine theta, the first times the derivative of the second, plus f prime of theta sine theta equals, divided by the derivative of the, well, we got the first times the derivative of the second, which is negative sine theta, plus f prime of theta cosine theta. So that's how do we find the slope of the line tangent to the curve of a polar graph. And it's right here again, provided that dx d theta does not equal 0 at some point r theta. Okay, so we take a peek at this. Here's a curve. You know, it's just not a normal curve, but you know, polar form gives us a variety of different curves. Okay, and you can make the following observations from here. To find a horizontal tangent, all I need is for the numerator to equal 0, which means dy d theta equals 0. Okay, provided that the denominator doesn't equal 0. And to get a vertical tangent, which you could see one happening right here, a vertical tangent, dx d theta equals 0, providing that dy d theta does not equal 0. And finally, if dy d theta and dx d theta are simultaneously 0, we can't make a conclusion. So if you have to check them both. If you just check the one and say, oh, it equals 0, but the other one also equals 0, we can't make a conclusion at that point. So be thorough, be checking both. All right, let's find the horizontal and vertical tangents of this equation, r sine theta. Begin by writing the equation in parametric form. X equals r cosine theta, but r is right here. That's that function. So it's sine theta cosine theta, and y equals sine theta quantity squared. Now we differentiate both x and y with respect to theta and set each derivative equal to 0. And you can see that happening here. dx d theta, cosine squared theta minus sine squared theta, which is a double angle formula, which you may or may not know. It's good to have those handy on that sheet. And so when does that equal 0? When theta is pi over 4. And just a reminder, cosine is 0 at pi over 2, so cosine of pi over 2. But if it's 2 theta, we have to divide that by 2, so we get pi over 4 and 3 pi over 4. dy d theta equals 2 sine theta cosine theta, another double angle formula. That equals 0 in a similar vein when theta equals 0 and pi over 2. So you can see here we've got a horizontal tangent, another horizontal tangent down here at 0 and at pi over 2. And we've got one at pi over 4 and another at 3 pi over 4. Okay, and to go ahead and do that, we'd find that point. We'd go back and find r cosine theta. If we go back, my equation was right here. Here's my function, r sine theta, and so that's what those values are. Right in here. So the r value is square root of 2 over 2, theta is pi over 4, etc., etc. Okay, that's where those come into play. Now I want you to find the horizontal and vertical tangents to the graph of r equals 2 times 1 minus cosine theta. I'm not going to do all this. Let's go ahead and just get it started so that you make sure you're on the right path. And really all I'm going to do have you say is, what is x equal to then? Well, remember x is r cosine theta. And so here's my r value. So we put that in there. 2 times 1 minus cosine theta. Okay, times cosine theta. Which, if I just keep going, gives me 2 cosine theta minus cosine squared theta. Now, that's in simplified form, but I'm not sure that helps us much. Oh, sure it does. That's my x value. We have to take derivative, so we'll do that in a sec. And the y value is going to be r sine theta which is equal to 2 times 1 minus cosine theta times cosine theta, oh, excuse me, sine theta, which is equal to 2 sine theta minus 2 cosine theta sine theta. So you might want to consider some double angle formulas here as well to help you out and maybe make that derivative just a little bit easier. But at this point in time, what would we do next? We want to find horizontal and vertical tangents. Horizontal, we're going to find the derivative here, but that's dy d theta over dx d theta. So horizontal would be when dy d theta equals 0, vertical when dx d theta equals 0. There's a lot of work involved in here. We're just going to keep it rolling. I've got other things I want to show you, but I want you to work on that. Come talk to me if you have questions on how that works out. Here is the solution, by the way, and you can see that you get all these fun little shapes, including this little point right here that we need to consider as well. But you can see vertical tangents here, and horizontal tangents here and here. This shape is called a cardioid, and I'm guessing you can figure out why. Looks a lot like a heart. Okay. Tangent lines at the pole. If f of theta equals 0 and f prime of theta, excuse me, this is alpha. F of alpha equals 0 and f prime of alpha does not equal 0, then the line theta equals alpha is tangent at the pole to the graph of r equals f of theta. Here, the zeros of r equals f of theta can be used to find tangent lines at the pole. We can have more than one tangent line since the curve can cross the pole more than once, and you'll see an example in just a minute of a bunch of these. So let's see how this works out. Okay, so when does this equal 0? Is my question, because that's what I'm going to need. So obviously we can divide by 2, and that works out to be cosine 3 theta equals 0. And the cosine function equals 0 at pi over 2, at 3 pi over 2, and so forth and so on. But this is cosine of 3 theta, so we're going to have to say that 3 theta equals pi over 2, which implies that theta is pi over 6. And same thing here, 3 theta is equal to 3 pi over, that's supposed to be a 2. So if I did that, I'd get 3 pi over 6 is equal to theta, which is pi over 2. And we would probably have a few more that would come up there. So then we have to also look at saying, to make it be a radial line, we have to look at its derivative, and show that it doesn't equal 0 at that point. So now we're going to look at, and these aren't exhaustive, these are just the first two. So what is f prime of theta? That's equal to, it's going to be negative 2 sine of 3 theta times the root of the inside using the chain rule, which is 3. So that's equal to negative 6 sine 3 theta And when does that equal 0? Well, sine function equals 0 at places like pi, at 0, at pi. So let's just take a look at a couple of them and we could be more exhausted. So if it's 0, 3 theta is 0 means theta is also 0. 3 theta equals pi would mean that theta is equal to pi over 3. That's not one of our answers, so we'd continue going in this vein to see how many solutions we'd wind up having. So go ahead and keep trying that. Alright, we've got some cool special polar graphs. These are called limosons, and they happen when you get the equation r equals a plus or minus b cosine theta, or r equals plus or minus b sine theta. Okay, and you get these cool little graphs that look like this, and the relationship between a and b dictate whether it's going to have a loop in the middle like this, it's going to look more like this dimple right here, if it's going to be a cardioid or a convex limoson. Okay, we've got some cool ones here as well. I want you to see these rose curves, which are fun. You can make them on your calculator, and I'll show you in just a sec. Notice here, if n is odd, it will have n petals. If n is even, this n value right here, if it's even, it'll have 2n petals. Right? All right, I just wanted to show you a couple things that you can do on your graphing calculator in the last couple minutes we have. And here, what I've done is I've hit the mode button, and you'll notice I'm in polar form instead of in function form. Okay, enter that. Go to my y equals, and you'll notice I get, instead of x and y equals, I get r1 equals. So let's put in something like 3 plus 2 sine theta. I don't know. We'll try it. Let's see what that graph looks like. Well, that's not so interesting, right? So what if I put in something like 3 plus, not 3 plus, but 3 times. Let's just put this in as, scoot over if we could. Delete that. We'll do 3 times sine of 2 theta. Let's see what that looks like. And we have some problems with our graphing on here, of course, but that's kind of a cool curve. And if the smaller step I use on there, so if I go to my window, you can see my step is 0.13. If I would change that to like 0.02 or something, it'd take a while to graph, but you'd see a pretty cool graph and it would look pretty nice. So you can play around with this. I love doing that. You can do some shading, put a couple graphs on there, see how they interact with each other. Go ahead and do that, give that a rip, and enjoy your graphing.